So these are ideal parameters that we want in a photoresist, but there's always trade-off with different parameters in terms of what is the reaction that occurs between positive resist and negative resist. There's basic difference in the chemical reaction. In case of that results into difference in the contrast that we can get from flow resist. So it's the change of solubility per change in irradiation dose. So how does the solubility change with the dose? So there's a figure of merit. It's called gamma, and it's measured experimentally by having different layers, different thicknesses of layers, and looking at how do the dose change those thickness. So what we do is we expose to the certain thickness to certain dose, and then we, after that exposure, we see how much is left behind, how much is it that has not been exposed. So let's see, I have. So in case of negative resist, what is unexposed, that is thickness 0. So at the start, it is 0 thickness. So as the cross-linking occurs, our thickness increases with the dose. And cross-linking is nothing but a chemical change where different subunits of a polymer would start linking to each other and making a connected network. So it's a chemical change from smaller subunits of a polymer changing into longer chains. And longer chain molecules are, what do we call long chains of molecules? What do we call long chain molecule materials? Polymers. Polymers, right? So single subunits result into this cross-linked chains. So longer network of interconnected subunits, and we call those long chains of molecules as polymers. So that liquid or resist material that we use, we call them polymers because they ultimately result into long chains of molecules. So cross-linking is what would start from top, will continue till the wafer, till it gets to the wafer. So in case of negative resist, this thickness increases as the dose increases, right? So the basic difference is in negative resist, this changed region starts developing from the top, but in case of positive resist, that starts developing from the bottom. So in another case, there is already a thickness which is available. That thickness goes on decreasing as the exposure continues, as the dose continues changing the resist property. So increasing dose decreases the thickness. So as it continues, so this thickness keeps on going down because more and more part of it changes chemically in case of positive resist. In case of negative resist, this change occurs from top to bottom. So this thickness increases as the dose increases, right? So these are two ways of looking at it. And at the complete dose, this thickness in case of positive resist gets to 0. In case of negative resist, it reaches the whole thickness of the resist. So now if you think about it, if the resist has to change from bottom up, you get much more better contrast than if you start from the top down. And this comes from the slope of the sidewall that we get at the end of the exposure. Gamma is a function of that slope. So if we start with same thickness of positive resist and negative resist, the reaction that occurs in both cases is essentially can be defined in a similar terms, because there's a chemical change due to exposure to UV, and change is cross-linking, right? So in case of UV, in case of positive resist, the areas that are exposed, they become soluble, right? So they are basically changing into something that will go away. In case of negative resist, they are cross-linking and becoming, in case of negative resist, the resist part that becomes exposed, it becomes what? Hard. Becomes insoluble, right? Because dwellement is not an etching process, it's a dissolution process, reaction which results into removal. So in both cases, the sidewall what we get of the pattern is different. We can get much more straight sidewalls for positive resist than negative resist. And gamma is what defines that. So the behavior of the resist during the chemical change defines what kind of features, how small of a feature we can get out of same thickness, same dose. But only the difference is one is negative resist, the other is positive resist. And that is something what we measure from developed film thickness after every given dose. So these are normalized, so we can compare them directly. In case of positive resist, we define this gamma as the slope of this line, and similar is the case for negative resist. So what it translates to is, with exposure energy, how deep can we go and what kind of profile do we get at different energy ranges. So at certain energy range, we get a very steep profile for the thickness. So from the original thickness to the end thickness, we can get the whole thickness of the resist to be exposed, which means it would have gone chemical changes, which is not the case. Here the slope is much less steep than in the case of positive. So x-axis is the exposed energy. I get a feel of.
Can you explain it again why negative resist is much what can I say, sloppy than positive resist?
Yeah, I'm going to take a step back here. So, in positive resist, our reaction is going to result into resist becoming soluble, right? In case of negative resist, exposure is going to result into becoming hardening or cross-linking, which is going to make it insoluble, right? So rest of parts will become dissolved. Now, in case of positive resist, on this side I keep positive resist and this side I keep negative resist. The reaction starts from bottom and top. In this case, it starts becoming insoluble from the bottom, and the thickness reaches all the way to the top. And then the whole region is become soluble. In case of negative resist, the cross-linking starts occurring from the top, right? So it has to get to the bottom before the whole negative resist becomes chemically stable against getting dissolved, right? How do we define the resolution? In terms of gamma. And gamma is a factor of the slope of this curve, which is between film thickness and the thickness that gets exposed, right? So this is what gives us this factor gamma.
Is it the border of the soluble and insoluble regions?
It's not the border, it's during that whole conversion, what happens to the sidewall? How does the region or the sides of that exposed area changes? So in case of negative resist, the change is much more pronounced on the sides. So you get a much wide sidewall which has much more small angle. So you get sidewall like this. In case of positive resist, you would get sidewall which would be much more at a right angle from the surface.
What's in the horizontal axis?
Horizontal
What
axis?
is the horizontal axis of the curve?
Oh, this is
The vertical axis shows the thickness.
this is also thickness. That's the dweller thickness. This is the actual thickness of the resist that we start with. Because at the onset of the process, the thickness is 0. There's no area which is exposed, and that keeps on growing. In this case also, there is the starting region is the whole thickness, and then it goes to 0. So we start with physical thickness, and then there's conversion occurring to some part of that thickness. But the bottom line is that at the end of the process, we see that at a given energy, the exposed region to the unexposed region, the ratio is much steep. We can, above this energy, you can get the whole region to get exposed very quickly with respect to the thickness, which would make our sidewalls much steep.
So in the first curve, the plot A, that means there is a limit in the actual thickness. There is a minimum limit of the photoresist thickness that has to be
That
done.
was on the previous slide. The explanation of these things was on the previous slide. That you start with unexposed thickness, which is 0. In this case, you start with the unexposed thickness, which is the actual thickness of the resist. So in both cases, our thicknesses, frame of references are different. In one case,
Boundary conditions are
pardon?
boundary conditions are different.
Yeah, because the reaction is different. In one case, it's making it soluble. In another case, it's cross-linking it. So, which side it starts from is different. Both cases, right? So, just hang on when you'll see much more explanation on this. So, higher contrast gives us, and contrast is where we can discriminate one color. In case of example of a television, this new high resolution TV set, we can discriminate black from white in a very clear way, right? So that gives us high resolution. So the pixel size is small, so we can have the white areas to be very clearly distinguishable from black areas than if the pixel size was bigger. Same is the case here, that the contrast gives us better resolution. This one.
You said in negative resist cross-linking occurs so that it becomes insoluble to the,
Right.
and in positive resist it becomes soluble. So are the bonds being broken in the resist? That
Yeah.
is
So
what's happening?
what's the reaction? Okay. The cross-linking also occurs in this case. In both cases, there's cross-linking. Okay. But in this case, the cross-linked polymer is soluble than non-cross-linked polymer. There is not just cross-linking, there is formation of acids also. There is conversion of materials into others. If you remember last time we saw chemical amplified U. So there is chemical change occurring which results into the resolution.
So it's not the bonding between the molecules that makes it hard.
It's the bonding, it's the chemical conversion that makes them soluble. So cross-linking, okay, that's a basic understanding of cross-linking is a process in which small subunits become part of a longer chain. And they can be intermediate atoms or molecules which help in that cross-linking process. So they become integrated into the polymer, right? So the new polymer, new long chain may have different chemical properties than before.
Okay.
Right? So in those cases, the UV exposure results into conversion into carboxylic acid, which is easily dissolvable in development. So what we are getting at is that if we start at the bottom, we are getting all the energy consumed. We have very less reflection, which would cause into the exposure exceeding the spatial limit. Exposure going away, because if light starts reflecting within the resist, what you get is something like this at the edges. But what we want is a step function, right? But we don't, it's an ideal situation where you get step function. What we want is something close to ideal condition, something which can be as close to ideal as we can bring it. We get this from positive resist. This is the case of negative resist, right? Because it's the basic idea of the change in the property is what reflects into the side walls being having smaller steps in it than a sudden change into the exposure. So this is what we call ideal, and this is what we actually get in case of negative resist, in case of positive resist, right? So our walls are much more steep in case of positive resist than what we get from negative resist. There's another function that we define as the resist modular transfer function, which is basically the comparison of how much of the resist converts into, chemically changes into the dissolvable or insoluble form. So it's a factor which is given by the maker of the resist. So seldom we calculate these things. So this is given what is the CMDF for a given substance, for a given photoresist. And ideally we want this to have value closer to 1. So these numbers DC, D naught come from that same first slide, which tells you the starting thickness and the ending thickness in both cases. Right? Okay. There are mechanical issues with resist. They swell. During development, they can expand. And what this results into my feature size? What can happen to my features?
What's the question?
If photoresist swells during development, what happens to the feature?
Increases.
My final feature size will have variations which are uncontrollable. And of course, it will expand, but the resist will expand, which will make my feature smaller, which is good, right? But it's uncontrollable. I don't know the variation, right? So we can't handle that. So that was also an issue with negative resist, where they would always swell below certain below 2 micron size. What can we say about making a line and making a circle in resist? So, a line and a hole, they are easy to define in negative resist, and holes are easy to define in positive resist. Think about it. What do we do? What do we get at the end of the process when we use negative resist? Where do we have, so if we are defining a line, where do we get resist left behind? In the exposed part, right? And we have only this region which is clean of resist, and it's a linear shape, right? If there is swelling, it can happen in partial regions, but would not be uniform all over the length. But if we have a circle and it swells, what's going to happen to the circle? It's going to expand from all sides, it's going to decrease the size. So in positive resist, making a circle is easier. We can have many of them closer to each other than we can do with negative resist. Of course, resolution, we would want thinner resist, right? We want thinner layers of resist. But what we do is we use the thickest possible so we can cover the steps and we can have good coverage at the corners of steps. And that is, I'll show you some pictures also. Corner of steps are important because if you are etching, if ultimately you're going to etch and you have something like this, your resist will have profile like this. So in etching, you might have resist. You might have etching seep through and attack the underlying, which is supposed to be protected. So what we want is we would use the maximum thickness that we can use for that particular process that we can, just to cover the steps uniformly. Sensitivity. Now, sensitivity, how many photons it receives and how many gets used up, right? So ideally, what would we want? Would we want to waste some photons? Like we don't. We want, if we don't use any photon, then we can reduce the overall dose, right? If we reduce overall dose, we can reduce the internal reflection. So we are giving in less number of photons, so there's less light that is traveling away from where it's supposed to be. So this is a figure of merit which is different for different resists, and the sensitivity, the gamma value also changes with that. So with sensitivity, your contrast also changes, right? So increased sensitivity would allow shorter exposure, which means less dose, right? And we can get exposure done less than 10 seconds. So what does it mean by less than 10 seconds?
Fast shutter.
Shutter speed, or what do we call that? Shutter size or shutter speed?
Duration.
It's duration, it's the speed, right? How quickly you open and closes. So we can maintain something which is below 10 seconds. That would increase our throughput, right? We can process many more if our exposure time is small. Right? It's not just how many we can absorb and use to do useful work, it's the wavelength as well. Of course, we want our resist to undergo chemical changes in the wavelength that we have, right? Have you ever heard the word monochromatic light? What is monochromatic light? Single wavelength. Where do we use that?
Yes.
Lasers, right? but laser is not cheap. Right? Our lamps give us pretty reasonable, what you call, band of wavelengths, but these are not monochromatic light sources. They give other wavelengths. But what we want in our resist is to be sensitive only to the wavelengths that we want it to. Right? So, but do we want it to be 100% sensitive? No, we don't want it to be greater than 40%. Why? So the rest can penetrate through and keeps on moving further to the deeper layer, right? So we want to get what is absorption. How would we of course, this is misleading that if we have a thickness of layer, we want the 100% to be absorbed, right? How do we define absorption? Yes.
If it passes through, and there should be a certain limit after which it will not pass through.
I didn't hear you.
Oh, I mean, if the wavelength, if it passes through, then after a certain limit, it might not pass. So
It might not pass.
pass through. So
Something called attenuation of signal, right? So what happens when a signal gets absorbed? Let's talk about area, antennas, electromagnetic. What happens when a signal gets absorbed?
Power or energy
So the power attenuates, right? So the signal gets consumed, so the power, basically energy, gets transferred to some other form of energy, right? If absorption is 100%, the whole energy will get absorbed at the first layer of photoresist it encounters. And it's going to convert into other form of energy, which is making it soluble, causing that reaction to occur, right? But we don't want the whole. We want some to travel through further down, so it can get absorbed over the whole thickness of the resist. Does it make sense?
So how do you make it 40%?
How do you make it 40% absorption?
How do you
How do we measure absorption in different liquids from different wavelengths?
But it's the same wavelength, right?
Right. So if I have a liquid, right, and I want to measure how much of certain wavelength will be absorbed in it, what do we do? It's something which biologists are very comfortable. They use that equipment. It's called spectrophotometer. Right? I don't know if that's exactly what's used, but that's where we fill up our cuvettes, small tubes, where the length is known, how much light will pass through once it goes through, and we strike a range, a spectrum of lights, and we measure on the other side how much of that light is coming through. So the wavelength that doesn't get absorbed, you get the whole thing on the other side. So you know nothing get absorbed, and then you see the spectrum and you see which wavelength got absorbed. You didn't get it on the other side. But can you change that? Yes. Add some more chemical, some other chemical, and change the optical properties of that liquid. Right? So chemically can change that. So we want this to have very important to read this graph. What does this graph tell us about this time? What wavelength do I want to use with this guy?
Between 250 to 300.
Okay, tell me, what wavelength do I want to use with this guy? So this would be 275, this would be maybe 280, right? I want to use 280 nanometer wavelength. What optical system gives me 280 nanometer wavelength? Yes, I line, G line, and then we started noting them by their wavelengths, those systems. There's no system which gives you 280 nanometer. But which one is the closest? It's steep UV, of course, it's steep UV, but you have to know the wavelength, right? fortunately or unfortunately, this comes in diagnostic. This photolithography is part of diagnostic exam, which if you're not a PhD student, you don't worry about that. But
I'm not sure it's probably argon filtering.
so, as a designer, I have to see this plot of absorbance for that resist, and I have to then decide what optical system I need, what wavelength do I need to do my lithography. Right? If I use 300 nanometer system or maybe 310 nanometer, will I get my exposure? Will I get my exposure? Guys, look at the plot. This is an essential exercise. If I have a system which has 340 nanometer wavelength and I have this photoresist and this is the plot of absorbance, can I do my lithography?
No.
Why not?
It won't reach the bottom.
It won't get absorbed at all, right? I know y-axis are arbitrary units, but it shows you that it's almost close to zero, right? Or whatever the minimum amount is given there. So we need to choose, and we need to know our resist and what lithography wavelengths, what optical wavelength do we need to do our exposure. But then they add the sensitizer and other chemicals which we can change the response to different wavelengths. So that sensitizer is what's going to change the response of that resist to that wavelength.
So it can become absorbent at 350, that's what.
Yeah, so it's different depending on sensitizer, right? Because that is going to cause absorption now in that film. Once it gets absorbed, you have that energy available to get your reaction done.
So at 250 there is a peak and a valley at the same time, so what is that?
So which one is greater in magnitude? That's going to take whatever it's going to do,
Okay.
right? So absorbance and chemical reaction. So first step is absorbing. So if it can't absorb it, so if you absorb that light at that wavelength, now your reaction will continue. Reaction will happen. So side note: if I have photoresist on my wafer, can I take it outside in the sunlight? No. Yes. No. Yes. No. It doesn't matter because the dose is too small. Dose is too small. Yes. Yeah. Theoretically, yes, we might have issue because there is whole range of wavelengths all the way from infrared to near infrared to all the way to whatever wavelengths are there. But the dose is too small. It generally doesn't hurt. But people like to wrap aluminum foils when they transport them. But generally nothing happens unless you're using very sensitive resist. What we use here is good enough to move around within clean room. Right?
So I have a question.
Yeah.
So for low absorption source, how about if we use high power source so we can condense it?
Yeah, so you can keep on doing your exposure for a couple of hours and maybe you'll get the whole thickness done. Right? Your professor will not be very happy. So yes, the idea is that you have to get the whole thickness to convert. So if absorption is low, you can do it for longer period. Theoretically, yes, you can do it.
Then that would be better quality, isn't it?
I don't know about that because you are exposing for a long time to this internal reflection which is occurring for a long time now. So maybe your side wall is too slanted, right? So I don't know, maybe. So we don't want the absorption to be close to 100. There are a couple of types of absorptions. One is exposure dependent absorption, one is exposure independent absorption. So when it converts, it becomes transparent, so which means the absorption keeps on going down. So what you get is absorption which doesn't contribute to exposure, right? So now there is what we call A and B, and C is what you defined as the absorption rate. So you have absorbance for exposed, you have absorption which doesn't cause any exposure, right, which is just loss of energy. So that difference is what will tell you, okay, where do you probably want to do your exposure, right? So there is light which gets absorbed but doesn't cause. So as I said earlier, there is absorption and then there is reaction. So your sensitizer will cause much more absorption to occur, right?
So exposure independent absorption is absorption will occur, but not the reaction in the photoresidence.
Not the reaction. It won't cause the what we call exposure, which is the conversion of resist into soluble form, positive resist. Right? So we have these numbers for A, B, and C. Now, for different wavelengths. Right? So these are system 365. So which one is I line, which one is G line? It comes quite often in final exams. So that will define what kind of process I want to use depending on these three factors. So you want A to be higher and B to be less to get much more efficiency from the exposure. And that results into dose, which is how much energy for how long you want to do.
So you first select your dose or you first select your sensitizer?
First select your dose and first select this. Unfortunately, you just buy a resist from manufacturer and you just use it. Because those systems have been standardized. So they know, you know, if I have a 360, if I have a G-line system, I know which resist I have to buy. So they are very standard. And if I'm pushing now and trying something, maybe something new, then I might have to see these detailed properties of my resist. But many times, for same system, same wavelength, you need a thicker resistance or a thinner resistance, depending on again surface coverage, how many steps you have, or what is the smallest feature size you want to make. Because if thinner resist, you can make smaller features. So, but it may be more stringent in how you handle it. What are the conditions you have to maintain in the clean room and all that. So I know at one time we had a very deep trench, so but the size didn't matter for us, so we used a resist which would give us 5 micron thick resist, just very, very thick for that class of resist. And but that gave us a good step coverage. I might have a picture of that as well. Okay, then we have to do etching. So most of them have good resistance to wet etch, and these Novolac and DNQ have good resistance to dry etch as well. But as we are going, some are becoming less robust to dry etch. So this is showing different polymers and their etch rate. Now looking at this plot, which one would be the ideal resist for me?
That has a lower etch rate.
That has lower etch rate. Okay. They have. Okay, I have this guy for lower etch rate, which is 2 dots, 1 line, 2 dots, 1 dash, PDACH. I think that's a good one. It has lower etch rate. So if I'm etching silicon dioxide, okay, now let's talk. If I'm etching silicon dioxide, which one of those is good for me? You said the one which has lower etch rate, right? Any other reason why would you want?
Yeah, the one with lower slope also.
Lower slope. The etch rate doesn't change over time. right? So the etch rate stays constant, because if all of these are good because their etch rate is going down, which is good, right? Because with time, we want it to become resistant to etching. So again, which one do we want to use? The one which has lower slope or higher slope?
Lower edge rate and lower slope.
Lower slope. And why we call lower slope? Because these are going down as they were,
So
right?
consistent.
So yeah, consistent is fine, but I want, if I have choice, I would want something where etch rate becomes even less after a couple of minutes or 3 minutes, right? So probably this guy, PDAP, is the best choice, which starts with same etch rate but falls very quick. But then it's still higher than this guy, so maybe PBM1 is best choice. I don't know. So
So
this
then
is,
it will depend what's my etch time.
it will depend on which one is available, which one costs better, but probably all of them can be good etch resistant materials, right? But you have to see how deep we are doing. So if my silicon dioxide etch is 10 micron, then how thick of the resist can I spin there? So maybe some of them can give thick films, some of them cannot, right? So there are many more factors that come into this. That's why you need professors to go and ask. So yeah, so this is etch rate for comparison and determination of selectivity of the polymers. Which one would you want to use?
So why the etch rate is decreasing? It doesn't make sense to me.
Yeah. So you have this top layer which is getting etched away, but you have the products coming out as well, which would cause self-passivation of that material itself.
So the residue like etch rate.
Yeah, the products are resulting into that self-passivating layer, which results into the. So you'll see that word, if you haven't seen that, the self-limiting etch or self-limiting processes where the products become resistant to further of that processing process, which we can use to our advantage. Okay, so etch resistance then shows with different materials, different recipes of etching. So in this case, this has been done with CF4. The etching has been done with CF4, with argon CF4, with argon CF4, C4F, 6O2CO. They all give us, you can clearly see that our resist has been clearly much more degraded in this case than in this case, right? And here we can see, we can still probably live it because it didn't do too much damage to this bulk, but at the interface, if we had maybe silicon dioxide or some other material, that would have gone bad, because this could go through it didn't etch the thickness uniformly, but it degraded that resist at many places. In this case as well, we have different recipes used against a photoresist that shows very, very different profile of that via. Right? So these are high aspect ratio etch, right, used for vias. Vias are where we connect different layers of devices with each other. So this is for 193 resist. Probably this come back again, so delete this. We want resist to adhere. We want it to adhere, so for many different reasons. For etching, we don't want any of that chemical to seep through, right? And how do we make adhesion better? We have to first get rid of all water vapor before we apply photoresist. So our soft bake has to be good. Shouldn't have any vapor. Those ovens are better which have air circulation. So they are continuously removing the whatever is coming off a resist from the chamber. So they continuously keep on removing water vapor or whatever comes out. We use a chemical called HMDS. So last time we saw that process of applying photoresist where you dispense it, right? So that figure was, the videos was probably the advanced automated systems. But generally what we do is we have wafer static, we don't rotate it. We put a puddle of resist, we cover the whole thing with resist. And then we start the spinning. Part of the reason is that the resist is a thick viscous solution, right? And if I'm doing it manually, I cannot be accurately in the center of the resist, center of the wafer while I'm dispensing it. So there can be weight imbalance on the chuck, and your wafer can go flying, because think about it, it's 4,000 RPM, right? So what I want is to, at stationary condition or very slow RPM, I want to apply the resist over the whole surface, make a puddle of resist, right? And then start spinning. So before I do that, I can do what we call HMDS priming. HMDS is a clear liquid, transparent liquid. It's silane based liquid. What we do is just put few drops and let it spin. It's transparent and very, very less viscous. So it dries up quickly, right away. Within 10 seconds it will dry away. So that has silane, which is silicon parts. They bind to the silicon substrate downward, and they have these atoms available for binding to the resist. I might have a slide on the video. So what they do is, what that chemical does is, it causes very good adhesion between. Some recipes may want you to do a bake on that wafer as well after putting HMDS. You make it to what we call curing the silane, which is making the bonds really strong. But there are many ways how we do that. We optimize the soft bake and PEB to get better adhesion as well.
What does dehydration bake like? You heat the
Dehydration to get rid of all the water content.
You heat the wafer for that?
Of course, it's bake. You bake the wafer. Yeah, you heat the wafer.
But how do you do that?
Maybe, yeah, good question. I should have. Let me make it. I think. This is, I'm doing it for my own reminder. Okay, there are few ways how do we bake wafers. One is using a hot plate. Hot plate is a plate. It's a small instrument which has plate, and you can adjust the temperature on the dial or electronic or digital or centigrade or Fahrenheit. So that plate is hot. You can place the wafer there. Some plates have vacuum suction points. So what you can do is place your wafer and start the suction there. Those vacuum ports are going to hold the wafer down. Because they're going to keep the wafer in very close contact with the hot plate. That's one way how we do it. Another is you can put them in a furnace. Furnace called, it's not like, have you guys seen oxidation furnace? It's not that kind of furnace. It would be a safe type of thing. You know, people have this safe where jewelers keep stuff. So it's a safe type of cubic thing which you put on desktop, and it has heater in it. And you can again adjust the dial to whatever temperature you want. Open the door, and you have these shelves like a refrigerator, and you place your wafer. Right? Close it and have this. either a manual thermometer or a digital display. So that's another way. And then there is this huge furnaces where you have high throughput going. So many people would putting their wafers in and taking it out. So you know, as I put my wafer at 9 o'clock, I'm going to take it out at 9:20. Right? So there are 2-3 ways how these are done. I'm sorry, I should have this. I'll get some slides on this. How do we do baking? How do we heat them? Now, all these different processes have their own pros and cons. In hot plate, the simple issue is that you have heat gradient. Now, yes, you have a hot plate beneath, but the top is exposed to environment. It's continuously cooling off, right? So, and if there is humidity in the room itself, so your dehydration bake is not happening because there's so much humidity. Yeah, you're getting rid of some, but then again, once you're gonna remove it, you're gonna get some wafers back on. So hot plate generally are dirty because multiple people are using it. It's an exposed platform, right? And especially if you use dual side wafers, SY wafers, where you have both sides which you want to use, then putting that I don't want to put my wafer on the hot plate at all because my lower side is going to get dirty. Of course, I can do piranha clean to clean it. Now, but it's quick. And then putting it in an oven, that's quick. But what is the downside with the oven? People put many kind of wafers going inside, so you never know what the other guy has had on his wafer who's baking in the same chamber that you are. Right? But an oven gives you a very consistent temperature inside if it's well maintained. But sometimes there is temperature gradient in the oven itself. Right? So in oven you can have multiple wafer carriers, multiple types of carriers that you can use. A single wafer carrier, the kind of the one which you guys have been given, single wafer carrier, right? That's what is that holder made up of? You guys have been given this wafer carriers. What is that holder made up of?
Teflon.
Teflon?
Not sure.
Not sure.
Plastic.
It's plastic.
Teflon. Yeah.
Teflon. Quartz.
Definitely not quite.
As you guys don't know your stuff here. It's supposed to be Teflon, as far as I remember. It's supposed to be Teflon. A Teflon can withstand high temperature. Teflon can withstand piranha solution because there's no glass in it. It's not quartz. If it was quartz, so you can put that wafer in your carrier and you can open the top and remove the lid and place it like that in the oven. Or you can use those boards where they're standing and you can put multiple wafers in them. So the hot air can move through both sides of the wafer. Right? So multiple ways how to be baked. So that is very important step, baking. Soft bake and PEB, both are.
What's your ambient when you're baking nitrogen? Because you don't want oxidation to occur.
You can't get, you can't. When you're heating it, even at 90 degrees, even if you're not heating, there's always oxidation.
So you can't.
There's no way you can get rid of native oxide. So we live with that fact, and that's why we always do PHF before we do oxidation. So we start with 0. But yeah, there's no way you can get rid of it. This is probably a repeat of previous slide. Viscosity. So we have solids in solvent to, which makes that liquid to flow, right? The resist has some viscosity. So 20 to 40% are solids, but that makes it hard to flow, right? And with time, that can change. So a resist that you use today at 4,000 RPM for 30 seconds, it gave you 300 nanometer thickness. 6 months down the road, that may give you 500 nanometer thickness. maybe 50%, 60, 80% more than what you got 6 months
It
back.
decreases.
Pardon?
So the viscosity decreases with time.
You have to store it in the right conditions. Right? That's the bottom line. It doesn't change as drastically as I'm saying if it's stored in the right conditions. But if your lithography fails, you might want to go back and see if that is the factor that caused underexposure and no development to occur. You know, once you do a development and it fails, it's very hard to see if it was underexposure, because underexposure means some part of it will get exposed, some thickness will get exposed, but not the whole thickness. It's very hard to characterize how much has been exposed and how much is not. So you have to then go back into your lab notebook and see 6 months back after 4,000 RPM and 30 seconds, how much was the thickness of this you were getting, and how much did you get today? And then that might be the deal breaker for you to correct your lithography, because now you'll have to have more dose, right? So this is very important factor of business. Many resists are just not meant for the process you're doing sometimes, because you might have high aspect ratio features and your resist will just fly off and would never go inside to cover those Frenches, right? So it would be too less viscous for you, right? So we have to see our application and have to know what resist will work for that specific application. Have you guys ever heard of SU8? SU8, write it down. SU8 is workhorse of MEMS. SU8-4X, which would be 4 numbers. There are different numbers that come. So there are different varieties of SU8, not varieties, different, I would say, models of SU8, so to speak. And those define what thickness you can get out of this resist. And when I say this is the workhorse of MEMS, we use SU8 to define high aspect ratio features to use it as a mold for PDMS, for other polymers too. So we make features, and instead of making features in the underlying wafer, we make features in the PDM, in the SU8 itself, and use those features to translate into microfluidics or translate.
It's kind of a polymer.
It is a resist. It's a photoresist.
So the feature is made in the resist and then
So
it is done.
because SU8 can give us very thick feature, it is very thick. If you look it up, SU8, you'll see that the come in 50 micron thickness, 100 micron, just very, very thick wafer. Your wafer that you're using in your class, how thick is that wafer?
275.
275 micron? Are you sure?
There's a tolerance, but the spec
Yeah,
says
but
it should be 250 to 300.
I'm fine, but with tolerance, but is that 275 microns? You can make a 200 micron thick wafer on top of that from SU, and you can make features in that. So that's something which is used. It's a very viscous resist. We can use it if we are doing deep RI in silicon, because now my resist, if I'm doing deep RI, I might be doing 300 micron deep etch. So I need a resist which is itself 200 micron, give and take, given all those other things. Given the selectivity is the same, 1:1, right? So these are new types of resists which have come, which are very viscous, and can use them for. But even if we don't get into this domain, you want to stick to those the positive resist. SU8 is negative resist, by the way. So it requires different mask and different approach. But probably we wouldn't talk about SU8 again, because it's MEMS when we are doing silicon fabrication. So for our wafers which have different texture, different features, we might want to consider what resist would be suitable for our application given. And the only thing we will be considering would be viscosity, because we might have trenches that we want to cover, might have raised objects we want to cover. Right?
That's resolution. How about the resolution? Basically.
Yeah. So in this case, I'm saying that at this decision, maybe just the viscosity will be what we'll be considering, because that will translate into how thick film can we get out of that, right? Okay. Now think about it. Somebody can say, okay, I can, if I have any resist, I can create any thickness if I want. Just all I need to change is the RPM and the time I spin it, right? Right? Yes, we can, but we cannot always expose all of those thicknesses given their wavelengths that we have for this, right? Because if we now try to do, yes, we can expose them, we do them for 2 hours, right? But then we can't get the features that we want. We can't get the critical dimension we want out of those, right? So, yes, one can always say, I can always play around and say, okay, I'm going to spin it for just 10 seconds and I'm going to spin it for just 2000 RPM and I can get thicker resist out of something that we use for 193 nanometer. But then your 193 will not be able to expose that thick layer in reasonable time. Even if it does, you will not get your desired thickness out of it. Does it make sense? Right? So it's not that we have just picked viscosity range and we are sticking to it. There's reason why we want to stick to that thickness that we get out of that. Right? We want to control the thickness that we make out of specific resistance, because above or below we won't be able to translate into a design. So this defines the thickness of given speed at given time, and centipoise is poise is the viscosity units, and we'll see changing viscosity, how does that change the thickness that we get out of a resist, right? So if I make it less viscous, I spin it, I get certain thickness out of it. If I make it less viscous, I can have more control over the thickness that I get out of it. Does it make sense? So this data is also provided by manufacturer, right? So, but they'll tell you this much RPM will give you this much thickness given you use this resist within the deadline, what we call expiry date. We still can get away using those beyond that, but then the viscosity might have changed. Right? So this is given by the manufacturer for the given viscosity, and it's much more that has been done. This is now the case with SU8. What you get is for which kind of SU8 is this? Doesn't say which kind is it, but there's 2 viscosities used, and what we see is these are in thousands. We can get hundreds of tens of microns out of that on the substrate. In this case as well, this is now 40, 60, so it's even less viscosity there. So viscosity is going down, so thickness is also going down. Overall thickness is going down, right? So this is data from a paper, low cost negative resist, SU8. I guess this is one of the early papers on SU8. Right? So viscosity has direct effect on what thickness can we make, and that is the thickness is now on the other side, factor of what optical system I have and what dose I can give out from that, and that will define if I can reliably expose that thickness. These are all things that we have to ensure while we are handling, while we are storing. We have to keep it clean. They generally send us with, and they give us low number of particle count, like this is less than this. But industry, they do their own filtration. Metals, they have to be very low because, of course, when you do bakes, you can get those metals to get incorporated into the wafer, which you don't want. Right? Flash points, yeah, you want lower flash point, right? Or not. These guys are sleepy. I'm saying lower flash point and nobody disagrees with me. We need lower flash point for resistance, or not? Says that we need it higher is better. So we don't ignite it doing bakes. And the TTV is what is the minimum limit of the nasty chemicals there in this, which can be worker can be exposed on a daily basis. So we want that minimum level to be a high number, right? Or not? Higher is better. So threshold should be low. Yeah,
No,
it should be
high.
Threshold should be high.
The maximum concentration to which a worker can be safely exposed.
So the chemical that we use should be less amount.
No, the threshold. The worker should be able
The-
to take as much as possible, right?
So threshold
Yeah.
should be high. Yeah. So it shouldn't be harmful even at higher concentration.
It's the concentration the
Yeah.
worker can take, not what's in
Yeah,
it.
it can be read in many ways, but we get the idea from this slide, right?
Where is the source of the metal content?
We don't want to have metal content in the resist.
Okay. So we cannot control metal content. It's just we purchase
Yeah,
for
yeah.
this.
Yeah, so
we want a low metal
Yeah. So we want to use something which doesn't have high metal content. But again, if you are just using it to make MEMS features, then you probably don't care, right? Because then you are not using for electronic devices out of that. But yeah, we want them to be low. So again, now a little more specific on the processing. So we clean the wafer, we do dehydration bake, right? We do soft bake, right? Apply HMDS, spin it, or there's a couple of ways how do we apply HMDS. I think I have a slide on that. But we apply HMDS and then we spin the resist, typically from 3,000 to 6,000 RPM, and for 30 to 40 seconds. But this is again what is given by manufacturer, what will give you what kind of thickness. We do pre-bake resist, 10 to 30 minutes for 90 to 100 degree, and we do alignment, we do exposure. Right? After exposure, we do PEB and we develop the resist. And after developing, we do post-bake resist to harden everything, harden the features. Right? So this is a typical process, typical run. And alignment and exposure will be part of the lithography too, which probably will start after the break. So what does dehydration bake does? It gets rid of moisture because your resist is hydrophobic. So your surfaces are hydrophilic, which is good or bad. So your resist is hydrophobic, your surfaces are hydrophilic. Will it work well, or both should be hydrophobic? What is hydrophobic?
It repels water.
Repels water. It doesn't like water, right? What's hydrophilic? If one of them doesn't like water, the other one likes water. What's going to happen?
One will try to get rid, one will try to keep water.
So it wouldn't stick, right? So you want to make hydrophilic site to get rid of all of water that's there, because so the hydrophobic resist can stick. That's why you have to do the dehydration bake. How do we measure? Let's not. How do we measure hydrophobic or hydrophilic property? This thing called contact angle pressure. I think we have covered that before, right? Yeah. So, moisture from atmosphere can cause de-wetting of resist while spinning. So, it can cause it to have water between the resist and the wafer, which is not good. Surface molecules are removed at 150 to 200, and those who are still hanging around, they go away completely at 400, but we can't go all the way up. What we do is we apply HMDS, and this is done at 100 degree, or you can just do it at room temperature. This is an example of a trench which is, I think, 300 micron deep, or not, no, it's 150 to 200 micron deep. So what it is doing is, photoresist is not covering the edge, right? So in this case, it still depends what do you want to get out of it, but it may fail the whole process. Maybe that didn't belong there. First. So how do we get? I think this is again repetition. Yeah, but this was the idea that you have silane where your one side HMDS binds to the surface, other side it has OH molecules for binding with the resist. That's again repetition. So okay, how do we do the HMDS application? Either we can spin coat it, which would be same way before doing resist, or what we do is we have vacuum chamber, small enclosure where we can put small containers which have HMDS in those, and place a wafer in the middle, close the top, suck the air out of that, and leave the wafer in those vapors of HMDS for some time, right? So that container will have those liquid HMDS, from which evaporation will result into the high concentration within that chamber, and they will stick to silicon surface. Right? So that is what we call a vacuum chamber application. The second is,
can we apply HMDS on any kind of surface at the silicon?
Any surface. What's the big deal? But towards what end? To apply photoresist? Yes. It's silicon dioxide basically. Mostly you have silicon dioxide or silicon nitride. So it works both ways, because you have silicon in HMDS which sticks to any silicon derived surface. So it can stick to silicon dioxide, silicon nitride, or silicon itself very well. Right? Let's stop here, because this is again